Throughout the history of our civilization on Earth, technological advancements for the benefit of mankind have required increasing amounts of energy. Increased energy from fire, from steam, from engines, and from electric power sources. Today, the need for more and more electric power transcends the Earth and follows man into space. At the beginning of the space age, satellites and space vehicles needed only a few watts of electrical power for short periods of time. Now, large spacecraft and complex satellites demand a much greater supply of electric power for time periods of several months to many years. The source to supply this need for electricity must be lightweight, long-lived, high-powered, and reliable. This source of electricity, a nuclear reactor, is available now. A flight test in space has been scheduled to obtain technical information for its use in space programs of today and in the future. SNAPSHOT is a cooperative effort between the Atomic Energy Commission and the United States Air Force. The SNAPSHOT flight will test the first United States nuclear reactor space power system. The power system is called SNAP-10A. Atomics International is the Atomic Energy Commission prime contractor for its development. For the SNAPSHOT flight, SNAP-10A will be shipped from the assembly area near Los Angeles to Vandenberg Air Force Base, California. In a facility near the launch pad, it will be checked out and prepared for flight. The system will be mated with the forward end of a Lockheed Missiles and Space Company Agena vehicle and supply electric power in space for scientific experiments. A heat shield surrounding the thermoelectric converter protects the reactor heat transfer fluid from freezing in space before orbital startup of the reactor. Covered by a nose cone, SNAP-10A forms the nose section for the Atlas Agena booster system. The system will be launched into a southward flight down the Pacific Ocean range. Shortly after launch, at an altitude of more than 100 miles, the Agena will pitch upward and the nose cone will be ejected. When a satisfactory orbit is obtained, the reactor will be started by radio command from the ground. Heat energy will be produced by the reactor and the heat shield will be ejected. A liquid metal alloy called NAC will transfer the heat from the reactor to a thermoelectric converter. The NAC is pumped by a thermoelectric powered pump. In both the pump and the power converter, heat from the NAC flows through thermoelectric elements and is radiated to space by small radiators. The flow of heat through the thermoelectric material produces a small voltage between the hot and cold junctions of the elements. This voltage causes an electrical current to flow. Current flows along each leg on the thermoelectric converter. The interconnected circuit of the complete system produces 500 watts of electrical power. The development program, which has resulted in the flight-ready SNAP-10A space power system, began over 8 years ago. Early emphasis was placed on the development of reactor fuel. The fuel is a unique alloy of uranium, zirconium, and hydrogen. As much hydrogen is in the alloy as in an equal volume of water, yet the hydrogen does not boil off at the high reactor temperature. In nuclear language, the SNAP fuel combines both a fissionable material, U-235, and a hydrogenous moderator in one substance. The alloy is formed into rods and canned in steel containers to become fuel elements. This type of fuel is desirable for space reactors since it permits a small, compact reactor core. Control of the reactor is accomplished by means of a simple mechanical motion of the neutron reflector surrounding the core. Operation of a demonstration reactor early in the SNAP program verified the reliability of the fuel elements. But the reactor, as the heat source for the SNAP power system, must be launched into orbit, start up in orbit, and operate for an extended time in the severe environment of space. A series of developmental and qualification reactors were built for testing. No shielding or remote control devices were necessary for technicians to fabricate and install the reactors. High temperature and vacuum environment tests were run to qualify the reactor for operation in space. Reactor resistance to shock and vibration of missile launching was established. Tests called critical configuration experiments measured the effects of various materials and liquids surrounding the reactor core. As we have seen, the reactor can be installed, checked out, and tested by personnel when normal industrial safety precautions are used. Radioactivity causes no handling problem because the reactor will not be operated at power until it is in orbit. When the SNAP-10A system is shipped to Vandenberg Air Force Base, the reactor neutron reflector will be removed and shipped separately. In place of the reflector, a sleeve will be mounted around the reactor core. The reactor cannot operate with the sleeve surrounding the core. When the shipping sleeve is removed at the launch site and the reflector is installed, blocks are inserted into the reflector to prevent accidental operation of the reactor. The extensive testing programs qualified the SNAP reactor for the environments of launch and orbit and demonstrated the inherent safety characteristics. Even though the eventual re-entry of the reactor from a long-lasting orbit presents no radiation problem, the reactor has been designed and tested for exposure to the destructive and disintegrating effects of aerodynamic heating when the system re-enters the atmosphere. Extensive re-entry experiments have been conducted on fuel elements. To demonstrate that the SNAP reactor system would disassemble when re-entering the atmosphere, a full-scale non-radioactive model of a SNAP-10A reactor was launched for the AEC by the National Aeronautics and Space Administration from its station at Wallops Island, Virginia, in the spring of 1963. This flight test was under the direction of the Sandia Corporation. The reactor model was instrumented. It was attached to the nose of a re-entry vehicle which contained associated telemetry equipment. The combined re-entry payload was mated to a Scout booster vehicle. The vehicle was launched during the early morning hours. The flight path was suborbital. At a descending altitude of approximately 46 miles, aerodynamic heating began to melt and disintegrate the reactor. Through extrapolation of data obtained from this suborbital flight, it is predicted that when exposed to re-entry heating, the SNAP-10A reactor would disassemble more than 40 miles above the surface of the Earth. In the SNAP-10A power system, the heat produced in the reactor is directly converted to electricity by means of thermoelectric elements. The development and fabrication of the thermoelectric converter elements was conducted by the receiving tube division of RCA. An alloy of silicon germanium was used as the basic material. Ingots made of the alloy were processed into pellets. Small discs were bonded to the pellets to form thermoelectric elements. Each completed element was checked for overall electrical resistance. The heat energy of the reactor is transferred to the elements by liquid metal flowing through a tube assembly. The exacting dimensional requirements for the thermoelectric assembly made this operation a major fabrication sequence. The tube, elements, and radiators were joined together by a special brazing and bonding process. A gold-coated shielding material was attached to the tubing to minimize the loss of heat. To obtain maximum radiation of heat from the top of the elements, a specially developed high emissivity coating was applied to the radiators. Completed thermoelectric modules were tested for all the environments of factory handling, transportation, launch, and operation in space. After acceptance testing, the modules were assembled into legs. The complete thermoelectric converter leg, consisting of 3 modules, was attached and secured to the converter structure. Highly flexible and well-instrumented prototype test systems were fabricated early in the SNAP program before establishing a firm flight design. These test systems were full-sized units, but components which were not needed for test functions were simulated by mass mock-ups. The combined results achieved from the entire prototype system test series established the system concept and provided the information for a flight design. But a flight design must be qualified. A series of qualification systems were fabricated and tests were scheduled. Tests that would duplicate the environments the flight system must endure from factory assembly through launch and orbit operation. The first qualification system assembled was non-nuclear. A full complement of thermoelectric converter legs were mounted to the structure. Complete instrumentation was installed. To assure that only components acceptable for flight were used, all components were subjected to strict acceptance testing before installation. Acceptance testing of the reactor included non-nuclear operation in a high temperature and vacuum environment. The completed system survived shake tests equivalent to the most severe vibrations of launch. Reliability of the integrated structural design was demonstrated. The system was installed on a test rig for operation at full design temperature in a man-made space environment. Nuclear heat was simulated in this system to permit any component relationship problems to be solved rapidly. Extensive test and analytic instrumentation was used to determine heat transfer characteristics. Simulated launch, startup, and orbital operation tests were performed using the Agena vehicle electrical equipment and telemetry system. This integrated test confirmed the overall system performance under orbital operating conditions. Another non-nuclear test system was assembled from fully qualified and acceptance-tested components. This test system was subjected to a complete simulated snapshot flight sequence, including a pre-programmed in-orbit startup. Following the simulated in-orbit startup, this system continued operation in an endurance run at design point conditions. A second type of qualification test system was assembled and used for an initial electrical checkout of the integrated satellite. The combined systems, SNAP-10A and the Agena, demonstrated satisfactory and compatible electrical performance during a simulated ascent and orbit operation. A second compatibility test system was assembled to provide a more detailed and extensive observation. Components on this system, necessary for final electrical validation of the satellite, were identical to the components used on the flight system. A third compatibility system will be utilized to check out shipping and handling activities. Pre-launch safeguards and procedures will be verified, and test handling on the pad for mechanical compatibility will be accomplished to assure correct and compatible procedures for the flight system handling. A nuclear qualification test system was assembled to identify any remaining problems involving nuclear operation of SNAP-10A in space. The test requirements were to demonstrate startup and satisfactory operation of the complete nuclear-powered system. A huge test cell duplicated to the fullest extent possible the actual environment of space for the nuclear startup and operation test program. Testing included simulated space orbit startups and full power operation. The qualification test series fully qualified the SNAP-10A system for the SNAPSHOT flight. The completed flight system will be shipped from the assembly area to Vandenberg Air Force Base. The neutron reflector will be removed from the reactor and replaced with the shipping sleeve. The sleeved reactor system will be placed in a double-walled shipping container. This container is air and watertight to protect the power system against shipping damage. Even the most serious highway mishap, in which the reactor might be surrounded by fire or water, could not cause accidental operation or spread of radioactivity. Escort cars will accompany the shipment 160 miles up the Southern California coast to the launch area. Launch activities for SNAP-10A, the first nuclear reactor space power system, will be followed by all news media and will be of interest to many. A part of the extensive effort which has made SNAP-10A flight ready is meticulous planning and thorough testing of all pre-launch procedures. SNAP-10A test systems and Agena mock-ups have been mated to check mechanical and electrical compatibility. A SNAP-10A test system is available for a test mating with the flight Agena after the Agena has been mated to the Atlas on the launch pad. Multi-step safeguard procedures involving void filler blocks and key locks have been established. Even improbable and unlikely accidents have been postulated, enacted, and analyzed to verify personnel safety criteria. The accidental dropping of SNAP-10A on the launch pad was simulated in a series of drop tests. Test results? No contaminant hazard to personnel if this unlikely event did happen. When personnel leave the pad prior to the SNAP-10A launch, the key locks which prevent reactor operation will be removed. Accidental startup of the reactor is then prevented by interlocked controls in the launch operations building. It will not be necessary to establish any special exclusion circle around the pad during launch. Excursion and other tests with the SNAP-10A reactor have verified that the exclusion circle already established to protect personnel from chemical fuel accidents is far beyond the exclusion circle needed to assure safety of personnel from any possible nuclear exposure. During all launches, a range safety officer has the capability to terminate the flight. For instance, if the launch vehicle should have a thrust or guidance malfunction and deviate from the prescribed flight path, it can be destroyed well within a predetermined safe corridor, which is clear of all populated areas. Today, missiles are rising successfully from launch pads, carrying non-nuclear payloads into space. The established launch activities for these successful launches need not be changed for the SNAPSHOT flight. Such a typical launch will carry the SNAP-10A system into orbit and build the foundation in technology needed for advanced space satellites. SNAP-10A will be launched southward over the Pacific Ocean. Almost immediately, it will be clear of all land masses. The booster engines will burn out and be jettisoned at 40 miles altitude and about 50 miles downrange. At 500 miles downrange, the Atlas sustainer engine will stop burning and the Atlas will separate from the Agena. Shortly after separation, the Agena will be fired. Flight velocity will increase, and the Agena SNAP-10A satellite will coast into an elliptical orbit. An Agena second firing will place the satellite into a circular orbit. This orbit will be achieved before any populated land is overflown. Ground receiving stations around the world will relay satellite tracking information to central control. All phases of the flight pattern will be tracked. When flight geometry has been established and calculations verify a safe and stable orbit, the reactor will be started by radio command from the ground. After startup and power stabilization is accomplished, no active control or moving parts are needed. The 500 watts of electricity produced will be used to operate instrumentation and scientific experiments in the Agena. At the completion of its assigned mission, the system can be shut down by ground command. The SNAPSHOT flight will introduce SNAP reactor power systems to America's space program. Systems that can be upgraded in power to meet tomorrow's advances in space technology. SNAP reactor systems typify the rugged and reliable power systems of low weight, of long life, that are needed for advanced satellites to accomplish improved international telecasting, weather surveillance, global communications, and many other beneficial applications. Finally, the SNAPSHOT flight will herald the great accomplishment to come: the manned exploration of an unknown frontier. The expanse of space invites exploration. But man cannot leave behind his Earth environment to explore this frontier. Man must take his Earth environment with him, or he will perish. Man in space needs air, heat, light, water, and food. Life support for man in space can only be furnished by electric power. The availability of SNAP reactor power units as a long-term, dependable source of electricity will provide man his life support for this dramatic and important exploration. Exploration that may discover new dimensions of human knowledge, dynamic knowledge that can answer profound questions. The origin of the Earth, the origin of life.